Brian.
Charles!
How are you?
I'm great. How are you?
Good. So there's been a lot of talk recently about functional programming, and a couple of the videos that I did from Jao,
Yes.
in particular Gilad,
Yes.
was talking about, Gilad Braca was talking about how monads could be used to solve, potentially a UI problem in Haskell.
Right. Absolutely.
So, of course, being who I am, an imperative type programmer,
Right.
was a little bit confused. And I know there's a lot of people out there. So why don't you take us through and teach us about whatever's on your mind regarding
All right,
monads?
I will.
Talk to us.
What I want to do is take the mystery out of monads. Monads without mystery, or maybe monads without misery.
Okay.
Because if you've looked at LINQ, or you've looked at F#, or a much smaller number have looked at Haskell, you've encountered monads, and they're scary the first time you encounter them. The main reason they're scary is you read the papers and they tell you, oh, well, you need to know category theory before you can understand this.
Okay.
And while that, strictly speaking, is true, it is not true that you need to know category theory to understand how monads work, what they're good for, and even better yet, how to creatively use them yourself.
Okay.
Let me talk about foreign languages for a second. If you want to learn French or something, there are sort of three phases that you go through. The first is you hear French and you say, oh my goodness, I'm scared to death of this. The second is you learn a little bit of French and you can recognize French words and you can read a little bit with a dictionary. And then the third and final phase is you can use it creatively in your own work. You can just speak freely.
Okay.
Those are the stages of learning any kind of new foreign concept. Monads are the same way. Everybody goes through this. The first encounter is horrifying. Here's this strange concept. And are you telling me I need to understand this strange, bizarre concept in order to do anything with functional programming? Well, yeah, the answer is yes. But what I want to take out of it is the strange and horrible part. It isn't strange and horrible. I'm going to explain it in terms of things you already know. I promise.
Okay, now I want to ask one question.
Yes.
And I'm probably going to interview Eric Meyer specifically on this topic, but you might as well touch on it a little bit. And that is, what the hell is functional programming in 3 minutes or less?
Okay.
Just quickly, so people get up to speed as to, they can then put the pieces together why monads would make sense in the context of functional programming.
Not only do they make sense, they're a natural outgrowth of functional programming. You would invent them yourself if you worked at it long enough. You wouldn't know the category theory, you wouldn't know to call them monads, you would just call them better functions. That's what I'm going to show you. But functional programming, in a nutshell, is programming with functions. That sounds kind of dumb, doesn't it?
Yeah, right on.
But normally, let me start scribbling on the board. Normally, we're used to doing things like this in C#. We'll say int x, and then we'll go someplace and we'll say, just for simplicity, let's make everything static. We're inside some class here, right? And we say static int f, and this takes an int x, and it does something with x, and it returns, maybe it returns some y that's inside the function. Let's make it do something here, like y equals math.exp of double x. It's already starting to look like a lot of stuff.
Yeah.
But the important part is we have a function that takes an int as an argument and returns an int as a result.
Okay.
Nothing scary there.
No.
Functional programming is taking these guys and saying, not only are these guys not scary, they're so ordinary that we're going to treat them just like we treat these guys. Okay. These guys are data. These guys are code. In functional programming, we just say, well, code is data too. We're not scared of it. Okay. Now let me introduce a little bit of notation. I'm going to stop writing C#. This is where it's going to get a little intense, but I promise it will all be things you already know. Great. If you know a function, you know everything you need to know to understand monads.
So look, a function takes input in, but always returns something, right? So that's what a function does. It does stuff.
Yes,
gives
it
you
takes an
functionality.
input, it takes an input
Yeah.
and converts it into an
Okay,
output.
so it's simple. And then in functional programming, that's your bread and butter.
That's your bread and butter. But the bread and butter is you just start tossing these things around as easily as you toss these things around.
Okay.
In ordinary programming, C# imperative programming, we think of data as being in one world, and then we think of these functions as stuff that operates on data.
Yes.
And they're special. In functional programming, we say they're not special. Functions are just like data. Let me prove to you that a function is like data. Every imperative programmer goes through this phase of learning that functions can be replaced with table lookups. Often you do this for performance. You want to create the sine function or the cosine function, just make a big table and interpolate in the table. You don't actually sit there and do formulas, right? Everybody learns this trick. What's a table? It's data. What is the function doing? It's looking stuff up. The act of looking up is universal. You can convert any function into a table lookup, and then the functionality, the code, is the same for all functions, and the function is just data.
Interesting.
There's your proof.
Okay.
That concept alone should convince you that functions are of the same kind of thing as data. They're not special. You don't need to have special code for every function, since it's possible theoretically to convert every function into a table lookup and to have the evaluation part, the code, be completely generic. Functions and data, data and functions, same thing. Think all noun-y, no verby.
So now, I mean, then I guess just quickly catch up, just so we get some of the confusion out of the way. When you think about the importance of, say, F# or Haskell and definitely
Yes.
Erlang,
Yes.
and in the multi-core world, which everyone's talking about right now,
Right.
it has to do a lot with the notion of no shared state, no shared mutable state.
That's right.
Now, is that just a consequence or a side effect of a side effect-free language, like a functional language? So let's talk about shared mutable state and functional programming.
Sure.
Okay. So quickly, I mean.
Yes. Pure functional programming, as in Haskell, does not allow any state at all.
Okay.
Functions, once you create data,
Yeah.
that's it. You've created it. If you say int x equals 5,
Yeah.
then x is 5 forever and ever.
Okay. Interesting.
It sounds like it's not possible to do much of anything useful with a language like that, but in fact, you can do almost everything that you can do.
Okay.
You can't do shared mutable state, but you can simulate it with monads.
Yes.
Ba-boom!
Okay. Now we'll stop talking.
No, you don't need to stop talking, because I want you to stop me any place where it's where I'm starting to get confusing.
All right.
I promise that I will explain monads in terms of things that you already know, and I'm going to go through 4 steps. One is functions.
Okay.
The second is monoids. You don't know the word, but you know what they are. Functions, again. I'll come back to them. And then monads.
Interesting.
And this stuff is easy.
All right.
It's conceptually very, very simple, very, very easy to explain, but you have to be willing to go with a little bit of a terse notation.
Okay.
Instead of saying int x, I want to say x int. And there's a very good reason I'm going to do this. This phrase up here says the variable x has type int. In mathematics, you'd say x is a member of the set of ints. Types and sets are almost exactly the same thing.
Okay.
I want to write it with a colon here because I want to put the types on the right-hand side. This is an assertion, x has type int. It means exactly the same as this. We're now leaving the realm of C# and entering the realm of F#.
Excellent.
Or the realm of functional programming. You'll see notation that looks like this.
Okay.
Now let me write the type of a function. A function, remember how I wrote it before, this was int f, int x, blah, blah, blah. Now I have a very compact notation. I can say int to int. A function is a thing that takes an int and gives you an int. That's all it means. Nothing more, nothing less. Next step. Instead of picking a particular type, let me pick any type. And I'll use the word A, I'll use the symbol A for any. Let me draw a line here. X colon A means I am asserting that X, the variable X, has type A.
Okay.
F colon A to A means I'm asserting that the function F takes an A and gives you an A, for A being any type. Now I'll go back to C# for one last little dive into C#. This would be, you'd say something like static A, how does it go? Generic, and what I'm trying to spit out here is generic type. Oh yeah, you say A, you don't put the brackets there. You put them here, oops, and you say A, X, A, blah, blah, blah. This is just shorthand for generic types. Okay. Stuff you already know. I promised you that wouldn't be anything you don't already know.
Okay.
We know types, we know generic types, we're not scared. We're almost to monoids.
Excellent.
Let me now kind of bang back and forth between these two panes. We don't need this anymore. Let me add another function down here. This is a function g, and I assert that my function g is a guy who takes an A and gives you an A. Now I'll go up here. Get rid of this. I now want to combine my two functions f and g.
Okay.
How can I combine them?
How can you combine them?
How could I combine f and g?
Make them one function? I don't know.
Yeah, I can make them one function. There are a couple of different ways of doing that. Let me show you one. One way would be to say, take g, feed it a variable of type A. Now I'm reusing the notation. The little a here means a variable of type little a.
Okay.
You'll forgive me for that. This is not at all confusing. This is call g with a variable of type A, and then call f on that result. That would be one way of combining these functions, wouldn't it? Another way would be to call f first, and then feed that result to g.
Sure.
Now I'm going to take away the brackets.
Aha.
The reason is they're visually annoying.
Yes.
Well, I'll leave this up here so that we're reminded that x has type A, f has type A to A, g has type A to A. In functional programming, we like to write function application, which means calling a function. Function application, calling a function, synonyms. I promised you, stuff you already know, nothing new.
Okay.
We like to write function application like this, GA. It looks like multiplication in ordinary mathematics. That's on purpose. Because if g is a linear function, and linear functions are special and happy and really cool, it is multiplication. So we make it look like multiplication for any function, even if it's not a linear one.
Okay.
Not only does this get rid of brackets, but it reminds us that in the case of linear functions, we have exactly this. Now, if I wish to, this is calling g with an argument of type A. Now I write my combination. This time I need brackets. I won't go into this. The reason you need one pair of brackets here is because of currying. Currying has to do with functions of multiple arguments. I won't get into it today. But suffice it to say, if I chain a bunch of functions together, it associates to the left. This is automatically, the brackets squeeze up on the left-hand side in this kind of functional notation. Okay. This is standard in Haskell and F#, nothing scary here, just something you have to get used to. If you want to call G first and then F, you have to write it this way. If you want to call F first on A and then G, you write it this way. Okay, these are two ways of combining a function. Let me now abstract. Let's stare at this one for a second. Suppose, let me invent a notation. I'll call it little circle. F, little circle G. This is a new function. And the definition of this new function is that if I apply this new function, F circle G, to the argument A, this is exactly the same as calling f with the result of calling g on a. This is a new function. I can now get rid of the a. I can't get rid of it on the right-hand side, but I can get rid of it over here, and I can give this new function a name. I can just say h is a new function.
Okay.
What's its type? We know the type of g is a to a. We know the type of f is a to a. I took an a, I gave it to a g, I get an a. I take an a, I give it to f, I get an a.
Yes.
The type of this thing has to be something that takes an a and gets an a. Look what we've done. We've taken two things of the same type, a function
Okay.
and a function, and we have created a new thing of the same type. That is the essence of a monoid. We're here at monoids now.
Okay.
The essence of a monoid is you have a way of taking two things of the same type and creating another thing of the same type. This is an immensely powerful concept. It enables you to create complexity starting with simplicity. I have a bunch of simple building blocks. I have a rule, little circle, for combining these building blocks in arbitrary ways. All that has to happen is the types line up, and I get new things of the same type.
So now let's step back real quickly and
Yeah.
talk about perhaps the usefulness of what you
Yes.
just did. So you
Yes.
took two functions that take the same type, return the same type. You've combined them into a new function,
Yes.
h in this case.
Yes.
Let's talk about what that means in the context of usefulness.
Yes. This is the way to build complexity. Everyone knows that one of the biggest problems in software today is controlling complexity. We add features, we interface to other people's features, we try to extend our software to other environments or other machines. We've got XML, we've got Ruby, we've got the web, we've got everything. And no matter, we find ourselves in this trap of extending our software constantly, and it's not doing anything new, it's just fitting to other stuff.
Huh.
We're out of control in the complexity space. The way to control complexity is compositionality. You step back, you create, it's a creative act. You step back, you create a design in which a number of smaller, simpler things. Now, let me digress on the word simple.
Please.
I use the word simple to mean small. Lots of people use the word simple to mean something else. So I try to avoid the word simple and I just use small. Because everybody agrees on what's smaller, but not everybody agrees on what's simpler. Some people use the word simple to mean more explicit, broader. Some people use the word simple to mean more concise, more abstract. That's why I avoid the word. But everybody agrees on what's smaller. The creative act of designing something, designing a software artifact in which it is easy to control complexity, is the creative act of creating functions that can be combined this way. This is called function composition. Little circle is called composition. And compositionality or composability, this is the way that you build up new things from things that you already have.
Excellent.
And remember, I began this whole talk by telling you I'm going to explain monads in terms of things you already know.
Perfect.
How am I going to do that? By combining or composing them.
Excellent. Now you use the composability word, and we've talked about that on Channel 9 a lot.
Yes.
Because
and its importance is going to increase as software gets more and more complicated. We need to have more and more control over the complexity. We need to be able to build up big spaces of rich software, but starting from simple building blocks.
Excellent.
And the way to do it, is to ensure that the types line up and to create yourself a generic composability operator that will allow you to take any things that are in your set of types and combine them and create other new things.
Excellent.
That are guaranteed to be in your set of types. Remember, we just calculated the type of H. We didn't have to assert it. It was implied by the fact that the type of F was A to A and the type of G was A to A. And the little definition of the composability operator, which remember was, well, it's written right up here. Take G, give it an A, you get an A. feed that to F, you get an A. Therefore, the type of F composed G must be A to A. There's no choice. Here's the beauty of this. If you discipline yourself and force yourself to put all your functions in this little type universe, then you can create new ones by composing them and be guaranteed that they will fit in the same type universe.
Excellent.
You can't make a mistake.
Excellent.
If you buy into the discipline.
And what that means then is you can change components anywhere in the system without destroying other parts of the system.
Glue them together, mix and match, make anything you want. You can start with a small number of things and end up with a large number of things, and they're all just correct by construction, at least in the realm of types.
Outstanding. Cool. All right.
All right. Now, we're in the world of monoids.
Yes, we are.
I'm going to give you a quick example to prove to you that you already know what a monoid is.
Okay.
And the example is a clock. I'll write it like this so I get my spacing right first time.
It's a good trick.
You already know what a clock looks like.
Yeah.
A monoid is a set of things plus a rule for combining the things. And that rule obeys some rules. That's it. You already know.
Can you say that once more?
A monoid is a set of things,
Yep.
or a collection of things to be more precise, plus a rule for combining the things.
Okay.
And that rule obeys some rules. Just two levels of abstraction here.
Got it.
Okay. In a clock, the numbers on a clock form a monoid. The rule for combining them is take one number, X, add another number from the clock, Y, and then cast out 12s, mod 12. Everybody doing C# or VB is familiar with mod operation. Now, you can take any two numbers. I can take 7 and 10, add them up, cast out 12, and I get 5. In the monoid of clock arithmetic, 7 plus 10 is 5. Because it's 17 minus 12 is 5.
Excellent.
The rule, this is the rule,
Yep.
composed of two things. And the rules that the rule has to satisfy are the following. Let me write the rule like this. This little symbol here stands for add the 2 and mod by 12 the constant.
Okay.
The rules are X combined with Y combined with Z is always the same as X combined with Y combined with Z. In any monoid, the rule for combining things must satisfy this meta rule. This meta rule is called associativity. It means doesn't matter how you group the applications. The second rule is the monoid must contain a special member that's such that X combined with the special member is always X, and the special member combined with X is always X. In the case of our clock, the special member is 12. If you add 12 to any number on a clock, you get the same number. 3 o'clock, add 12 hours, it's 3 o'clock again. Yeah, AM, PM, we're not talking about that. We're talking about a 12-hour clock.
Got it. Absolute number. Right.
Notice I carefully wrote the special member on the right and the special member on the left because one of the rules that a monoid operation does not have to satisfy is commutativity. It is perfectly allowed for X combine Y to be not equal to Y combine X. In the case of a clock, it so happens that X combine Y is Y combine X, but we already found out in our little function world, F on G of A is not G on F of A. Sine, cosine, cosine, sine, not the same thing. Anyway, the point of the clock is to show you that a monoid is a simple concept. It has, just to review, a set of things, numbers, in this case numbers, in this case functions. A rule for combining the things, in the case of a clock, add them and cast out 12s. And the rule has to satisfy meta rules. And the two meta rules are associativity and existence of this is called a unit or a zero, generically or abstractly. Okay, I'm going to erase the clock example because we've now locked this monoid into our memory because it's so simple.
Okay.
And I'm now going to go back to functions. So we're here.
Excellent.
And show you, I don't even really have to show you anything at all, do I? Because you already know the punchline.
Yeah.
Functions under composition form a monoid.
Yes.
At least if the types are the same over here. Now I'm going to just talk for a second, and I'm not actually going to write this down. I'll leave this as exercise for the reader, because I want to get to monads without this extra complexity. In full generality, we allow ourselves to have different types here. So we allow F to go from A to B, and G to go from B to C. And then we can only combine them in one way. In that case, they don't form a monoid, but they form a monoidal category. And that's where we go into category theory. But you don't need to know category theory to be fully conversant, to be fully fluent in this language of function composition. All you have to remember is the types need to line up. Everybody already knows this from programming in statically typed languages like C Sharp and VB. The types of if you're going to nest function calls, the types have to line up. There's nothing complicated about this. You don't need to know category theory to, if you want to learn category theory to understand the full flowering glory of these, of the consequences of this astonishing, you can, and by all means, it will only increase your richness. But you can now speak French in the world of monoidal categories because you understand, as long as the types line up, then compositionality makes sense. I'm going to stick with the simpler monoid of functions here. All the types are the same because they form a monoid, and it's absolutely crystal clear that just like a clock, once you go into the clock, you can't fall out. You can add 3 and 17 and 49 and 600 trillion, and you'll still get a number between 1 and 12. You can't make a mistake. Compositionality in clock arithmetic is exactly no more complicated than compositionality in function composition. This is the power of it. This is why compositionality is the thing that we need to know to control complexity. Okay.
Outstanding.
Let's prove that function composition is associative. That means F compose G compose H is always equal to F compose G compose H. Remember, I'm asserting that functions are in a monoid, just like clock numbers are in a monoid. So in order to prove that, I have to demonstrate that my little circle operator is associative. Or we just write down the definition. I can remove this. Let's add H to our catalog of functions down here. It's A to A. And we're conversant enough in this that we remember, in order to expand this out, I have to put in an actual argument. So what does G compose H mean? It means apply H to an argument of type A, and then apply G to that. Then if I compose F with that whole thing, that can mean nothing other than calling F like that. Now, F compose G means calling F on G who's calling something of type A. What's the thing of type A that G can call? It can only be H of A. There's no other thing of type A anywhere around. There's no possible way that function composition cannot be associative. Write it out yourself and see that it there's just no other way for this. It's almost trivial.
Okay.
It's associative.
Great.
Convinced?
I'm convinced.
All right. Last thing is we have to have unit. What's unit? Well, there is a specific function called ID It is of type A to A, so it lives in our monoid. And the definition of ID is that if I apply ID to any argument A of type A, it just gives me A back. If I compose F with ID, I have to write now arguments in order to say what this means. I call ID with an argument of type A. I then apply F to that. Since ID of A returns A, this is F of A. The definition of F composed with ID is F. And it holds true the other way around. I don't have to write it down. Functions under composition are a monoid. We're here, monads. What is a monad?
Right.
It's almost exactly the same as a monoid. There's only one little twist.
But it's probably a significant one.
Yes, but remember what I'm trying to do is teach you fluency so that you can use this in your own work.
Okay.
You don't have to be scared of it at all. I'll take off the right-hand side. I'm going to take this off. We're now going to leave the realm of functions that take A's and return A's.
Okay.
And I'm going to enter the realm of functions that take A's and return some transform of an A. It's okay, we don't have to be scared because we didn't do anything scary. All we did is say, look, my little universe of functions now, I want functions that take A's and turn them into M of A. This is really a type notation that means the type of the return value. This is called a type constructor. What it really means is that every function that lives in my little compositional universe will take an A and return some extra data applied to an A. This is some little function that lives outside, but it's the same function. This capital M is the same function for every F, G, H, and so on that's in my little universe of compositional functions. All I need to do now is explain compositionality. I knew what it meant when I didn't have this M. I knew what compositionality meant. What do I do with this M now? This M is kind of like the fly in the ointment. It's bugging me.
Okay.
Let me do it this way. I'm now going to use lambda notation. This is also not scary. Let me bump into C# for a second. In C# you would say A to mumble, mumble, mumble.
Yeah. Lambda expression.
Right. Lambda expression. In my little math notation, remember I said this is for intermediate programmers who are not scared of a little bit of theory.
Great.
By the way, in F#, in Haskell, we do lambda with a backslash. So just for fun, let me just leave off the little hook on lambda. That's the Greek letter lambda.
Okay.
I'm just going to leave that off. And in Haskell, you write exactly the same thing like this. This is a function that does blah blah in C#. This is the function of A that does blah blah. This is the function of A that does blah blah.
Okay, now in the syntax is the same. It's a string. Yes?
Yes, it's just a string. You just literally type
the guts
this in.
of the function.
Backslash A.
I mean the dot 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 part.
Oh, this is just whatever it does.
What if it's just the guts of the function?
Sine of
dot,
A
dot, dot.
plus A squared or whatever you want
Understood.
to do.
Understood.
And you do the same thing in C# up here. This guy, and again, I'm reusing the variable name to imply its type. This variable little a is a variable of type little a.
Okay.
And we're not confused because we know when we're writing types and we know when we're writing things. Same thing down here. Yes, I'm writing types over here. Later on I might say M of A to mean a function call of the constructor for type M. I use the same notation over here in the type world. This is a call of a function. Remember, function application looks like multiplication. This is M times A. This is calling the constructor of type M with a variable of type A. This is what I want to do in my new...
And it guarantees that it returns A.
Well, we don't know what M of A does.
Ah.
We don't have to say.
As long as it's the same thing.
As long as it's the same type everywhere, we don't care what it does. It could call a database, it could do I/O, it could launch the missiles, it can have arbitrary side effects.
Interesting.
Yes, yes.
Fascinating.
Now we're seeing why monads are really powerful.
Yes.
All we're really trying to do is bring the world of side effects under control. What's the control? Compositionality. Compositionality, the slogan is compositionality is the way to control complexity. The world of side effects is very complicated. I/O, concurrency, shared memory, yuck. Yes. Continuations, exceptions.
Absolutely.
Oh boy, no end of complexity available to you. SQL, interacting with SQL database. Link is a monad.
Link is a monad.
Link is monadic, yes.
It's monadic.
It was very carefully designed by Eric Myers so that it is monads in disguise. I may not be able to show that to you today, although I probably can. But if I can get to associativity, if I can get to composition, no, don't stop asking questions. Keep me on track. I want to show you that the compositionality that we have with monads is very similar to the compositionality we have with monads. We totally understand how functions under composition is a monoid and therefore puts you in a place where you can't make mistakes.
Okay.
Now we're going to go back to functions. We're going to add this little data here that hides all the complexity of concurrency, whatever we want. We don't say what it is. All we just say is its type is MA.
Okay.
I now have the problem, though, of composing functions that look like this. I can't do it the way I did with little circle because I can't arbitrarily nest them. But I can still do it. Let's say I have a function of A that does f of A. I'm going to change colors here now. What's the type of f of A? Well, we know that f takes an A and returns an MA.
Yes.
So the type of this guy is MA. Now, let me invent a new operator. Haskell calls this bind. I call it shove. And the reason I call it shove is what this does is take this result somehow. I'm going to bracket this in a second to show you exactly how it works. But it shoves it into something, let's call it a function of A that does GA. All right? We're not scared yet, right? Everything we've seen so far is familiar. F of A returns an MA. The type of FA is MA.
Mm-hmm.
This is a lambda expression. We're not scared. This is a lambda expression. We have an MA over here. Well, look, we've combined two things that are of the same type.
Mm-hmm.
The thing over here is a lambda of A that calls a function that returns an MA. The thing over here is a lambda of A that calls a function that returns an MA. In fact, just by itself, you can see that this lambda expression is rather empty, isn't it? Mm. Lambda of A that calls GA, why don't we just write that as G? We can. It's exactly the same type. The type of this entire lambda expression is a thing that takes an A and returns an MA.
Which is defined as G.
G is a thing that takes an A and returns an MA.
Yeah.
This lambda expression doesn't do anything other than call G on A, so it is exactly the same as G.
Okay.
The reason we write it in this contrived way is we can't do this over here, on the left-hand side of shove. We've lost a little bit of our symmetry. The reason is we have to take this FA and shove that in over here. The reason is this thing gets bracketed this way. The composition of these two functions is a function that takes an A and returns an MA. In order to do that, I have to take the MA and shove it into a function that takes an A and returns an MA.
So it's a lambda expression that has a lambda expression inside of its...
It has a shove expression, or a bind. You know, the Haskell guys are going to be puking. They're going to be rolling over in their graves.
All right, I got it.
But this is a shove expression on the right-hand side. But the result of the entire thing is another one of our guys. This takes an A.
Okay.
And as long as this bracketed guy returns an MA, then the result of shoving, I'll scribble here, is an A, is a function that takes an A and returns an MA. Now, I'm going to write the type signature of bind or shove here. This is where people get confused with monads, and this is how I'm gonna unconfuse you. The reason people get confused with monads is they look at the type of this operator bind, and they see that its left-hand argument is an MA, something that's in the monad,
Okay.
and its right-hand argument is of type function that takes an A and returns an MA. It's not symmetric. Why? Well, the reason is, in order to restore the symmetry and get back to the world of compositions, we just have to put one little lambda on the outside. And now the entire expression is back in our compositional universe. It's almost exactly the same as a monoid. In fact, as long as these types are the same, these functions that go from A to MA live in a monoid. And these data live in the monad. That's the definition. We want compositionality for exactly the same reasons as I said before. We want our functions to live in a monoid. But we need this extra data so that we can do concurrency and side effects and I/O and whatever else.
Make the program, make it useful. Make
it useful.
Programs.
Make useful programs.
Uh-huh.
So we need our data to live in monads, but our functions still to be compositional. And bind is the guy who ensures that your functions are compositional. You have to design this. When you're creating a monad, you have to design the implementation of bind. I'm not going to write one down for you. Maybe another time I'll go through the list monad or one of the other monads and show you how you design one of these things. But all I want to do today is give you the conceptual assuredness that you already know what you need to know. It's just a little accident of the fact that we have to add this extra little lambda on the outside to see the compositionality. But it's there. It's forced on us. If you take away the red stuff, then this entire thing looks just like the composition. Just replace this guy with a little, here, I'll just make a little red circle, I'll put an M underneath it. This is a composition operator. But because the right-hand side of the outer lambda has to contain all the rest of this stuff, many people just simply omit to write down this outer lambda. And then people get confused. They look at monads, they see the asymmetry, they don't realize if you stick a little lambda out here, it looks the same as composition. And so they never even see the compositionality. They just see this mutant bind operator, and they can't see why you have it or how it works or anything. The reason you have it is so that your space of monoidal functions is fully compositional. So we get all the benefits that we get from a monoid. But we also get all the benefits from a monad. Why? Why on earth would anyone do this? Well, the reason is exactly the reason you do it with ordinary functions. Control complexity. You need to be able to create functions that you can mix and match in any way. Because we need to create small libraries. We can't all afford to have 1,000 programmers bashing away on keyboards to create software. We have to create small libraries of compositional functions that can be combined in arbitrary ways so that our users can create new functions and not fall off the ship. You're guaranteed if you design this bind operator correctly, and by the way, this satisfies an associativity rule just like remember I said in a monoid, the rule has to obey meta rules. Same here. This is the analog of composition. The rule here has to obey associativity. So if you bind or shove F with G and then with H, it has to be the same as doing F with G and then F and then G and H.
Okay.
And you also have to have a unit. Guess what? Unit is a guy that you get to design. It's usually written in Haskell, it's written return. It has type A to MA. And you have to guarantee, when you design return, you have to guarantee that when it's composed with bind to some other function on either the right or the left, it doesn't damage it. It leaves it the same. Let me go back to link for a second and say MA in the world of link is I enumerable of A. We've just added some data to our A, added some stuff. We don't know what it is, we don't care. You can do arbitrarily complicated things as long as it supports I enumerable. Bind is select many. I invite you to go look at the signature for select many, and you will see that it is bind. There's an alternative bind, that's select. It's not necessary for the monoidal. I'm starting to, my board is getting cluttered here.
Looks, yeah, understand.
But I hope that I've given some clarity to this.
Yes.
Just to review, functions are not scary. They take inputs, they give outputs, and they are themselves artifacts that can be passed around as data. Proof? Think of them as table lookups. The table for a function is like the data. Compositionality is a way of combining functions. If you obey the rules of associativity and having a special member that doesn't hurt anything when you combine it, then you're guaranteed to be in a monoid and you can never fall off the ship. You can mix and match your functions in arbitrary ways. To get to a monad, you add this little data constructor, unspecified. All that matters is that you restore compositionality through a bind operator and a unit operator. Now you can understand link, now you can understand F#, now you can understand Haskell, now you can create your own monads to do anything you want. Probably the first monad, if you want to play with this, create a monad that does nothing. Where capital MA doesn't do anything to A.
Okay.
It just changes its type, but it doesn't change the content. That's called the trivial monad or the identity monad. And then convince yourself that functions that operate under this discipline compose. You can never fall off the ship, cannot make mistakes by composing functions. This is glorious. This is the way to control complexity. This is not arcana. This is not arcane stuff from category theory.
Yeah.
This is not stuff that only pertains to super pure ivory tower programming languages like Haskell. This is stuff that we need for link. How can one design, link, the standard query operators, work for SQL, for XML, for objects, for things that have completely radically different data models? The answer is, put them in it's a monad. The functions compose. You can compose them in any way you want to. They're good enough to give you all the functionality you need for query. Now, you can't do all the hacking that you can do in XML, but you can do query. You can have one query language that works over all these different data types. It looks like a miracle until you understand that what's really going on is you just say, you know what, I like this clock arithmetic because I can never make a mistake. Let me design my functions under a similar discipline. Associativity, left unit, right unit, done. Monads, no more complicated. Just add this little doodad on the side.
Interesting.
Did that help?
Absolutely.
Okay.
No, it's very helpful.
The last little thing, the last little fly in the ointment, remember when we talked about functions, as I said, you can allow A to go to B and B to go to C. You can do the same thing with monads. So we can put arbitrary things, so we can go A to MB, and we can go B to MC, and we can compose these things that way. This, again, to pursue the mathematics of this, you really do have to go to category theory, but not to pursue the intuition. You can use this fluently because every programmer already knows how to match up types and compositions. Just have to be careful with this bind operator to make sure that the types line up. You can't fall off the ship.
Now, however, I would say that from a conceptual perspective, there's definitely a little bit of a leap going from the monoidal interpretation or description that you had done.
Yes.
Because looking at that down here, MB doesn't. Why is MB the same as MC?
Oh, it isn't.
Okay.
It isn't.
But we did talk about earlier the necessity for all types to be the same.
Yes, because I wanted to develop with crystal clarity. You
Okay.
don't have the distraction of having to
Understood.
line up B's with B's and C's with C's.
Okay.
If everything is an A,
Yes.
then it works very simply.
Okay.
You can add a little bit of richness without adding a lot of complexity
Uh-huh.
by relaxing this. Let me write down the actual rules for bind in the case of relaxing.
Yeah, I think that would be helpful. At least for this numbskull.
I'll fight you for that title.
No.
Let's say that our function g, in fact, let me read, well, let's leave our catalog up for a second. Let's say that our function g goes from an A to a B. This is a type notation. I'm asserting that function g has type A to B.
Okay.
And now let's let our function f have type B to C. Then, if I compose them, and notice I'm writing backwards on purpose, because I want an A to come first and then a C.
All right.
This guy is a new function. I can give it a name if I like. I don't have to give it a name. This is a new function that takes an A, feeds it to G, then takes the result and feeds it to F. So let me write it. Now I'm writing an equal sign instead of a colon. I'm now in the world of values over here.
Got it.
I define this. This is defined. Now I'm going to write an equation that puts me in the world of values. F, compose G, applied to an argument of type A, is defined as F called on G called on A. G called on A has type B. F takes an instance of type B and returns something of type C. So we've got it. Look at that. We've composed F with G and gotten a new function, and we even know its type, and we know what to do. This is the code for F compose G. I could write this out in C#. Should I?
Yes.
Yeah, does that help?
Absolutely, actually, because most of the people watching this are going to be imperative programmers.
Yes, but functional programming is a style that works in any programming language.
Okay.
And it really works in C# now that we have lambda expressions. And we have them in VB too. And it really, really works in F# because in F# functions are first-class citizens and you can toss them around just the way you toss variables around.
Outstanding.
You can do that in C# and VB too, but it's a little more syntactically noisy because you have to use lambda expressions and maybe delegates, and then I get confused.
Okay.
Let me write this out in C#. So we said G is a function that takes an A, let's call it little a. Now I'm going to use capitals for types. Sorry about
Great.
that. And returns a B. And we don't care what it does. That's its type.
Mm-hmm.
And F takes a B of type B and returns a C. And we don't care what it does. And F, since I don't have a little circle in C#, I'll put a C. Compose G, well, we know that that returns a C, and we know that it takes an A, and now we do care what it does. What it does is return F called on G called on A. Pretty? Beautiful. Beautiful. Now, you can see why we prefer the tight, concise mathematical notation, because
that's kind of ugly.
well,
Pretty,
it's,
but
it's actually really, really beautiful. It's just a little noisier.
Yes.
There's just some more brackets and stuff in the way.
Mm-hmm.
Boil away the inessentials, and you're left with the essentials.
Yeah.
And that's by the way, that's all Haskell does. That's all F# is doing. It's just boiling away some of the syntax that you don't always need. You sometimes need this syntax, but you don't always need it. Mm-hmm. And if you're in the world, a very simple world of monoids, or monoidal categories, you don't need all that stuff. You just really want to think about it in this way. We lost something though. Remember, the topic of this segment is what do we do when not everything is an A?
Yes.
What we lost is we can't write down G of H. Scratch that. We cannot write down G compose F because the types don't line up. F, how would we write this down? Well, F takes a B and returns a C, but you can't feed a C to a G. We can't write it the way we did before because we have a type error. The type of F of B is C, and G takes an A.
Okay.
So we can't do this. This is a type error. This is a compile error. Compiler says no can do. So if the types are not all the same, we don't have a true monoid. It's a little bit like a clock where you're only allowed to add numbers in one direction. Maybe, I don't know, I don't want to push the clock analogy. Actually, maybe for another time I'll think of a good analogy just in terms of numbers and arithmetic.
Sounds great.
On the tips of my toes, I can't think of a good analogy.
That's fine. I mean, we shouldn't stray too far from...
But all I wanted to point out is we still have compositionality.
Okay.
Every programmer is totally comfortable with lining up types. And you can see that the metatype, the kind, to use the Haskell lingo, the kind of this guy is just like the kind of this guy. They're functions from thing to thing, and you just, if you want to compose them, you line them up, and you don't fall out of the universe of functions from thing to thing. We just have three different kinds of things here. We have an A kind, we have a B kind, we have a C kind, but our functions are still functions from things to things, and so it's almost monoidal. Good enough for programmer work. Good enough for conceptual hygiene.
Yes.
Good enough that anybody can be totally fluent in this without understanding the category theory.
Outstanding.
But this is a nice introduction to category theory. You want to go study it.
Yeah.
Thinking about things this way will make it much easier for you than it's not purely abstract. Now, let's go to monads of the same kind of thing. Well, we want an F that goes from an A to an MB, and we want a G that goes from a B to an MC. Did I change? Oh, I did. I switched F and G. Sorry.
No problem.
All I wanted to do was add the M's there. I wrote them this way on purpose so that F composed G is in alphabetical order. How can we compose these with our bind operator? Well, we want to have a lambda of A that calls G of A and shoves the result into a lambda of B that calls F of B. Whew. Nothing scary here. It looks just like this. Just looks just like function composition. The only fly in the ointment is just as before, we have to bracket it this way. But we're not scared because we can look at this guy and see that the type of this entire expression is A, takes an A, and returns an MC. Because F applied to a B returns an MC. So we have taken a thing that goes from A to MB. We've taken another thing that goes from B to MC. And we have gotten a third thing that goes from A to MC. Looks just like this. The only difference is, because of syntax, here I got to write F and G in alphabetical order. Here I have to write them in the order they appear. I'm still not scared. It's a small change. What I get in return is I get this monadic behavior, which is anything I want, as long as I obey the rules of associativity and a unit. Now, what's the type of the bracketed thing? Let me erase the... actually, let me just write it in red.
Okay.
The type of the bracketed thing, which is the type of this guy, is something that takes... G of A is MB. Something that takes an MB and takes a function from B to MC and returns an MC. That's the type of the red bracketed thing. That's the type of the bind operator. It's an infix operator that takes an MB on its left-hand side, takes a B to MC on its right-hand side. That's this lambda expression right here. Has that type, B to MC, and returns an MC. This is where people get lost. They go into the weeds when they first encounter monads because they don't see the outer A.
Mm-hmm.
Once you put that outer A on here, you realize that all that's going on here is just composition.
Yes.
Composition of G with F to give you something like this.
Absolutely.
There's just a little bit of syntactic trouble in here because of this fact that we have to have the lambda on the outer side and we need to describe the type of the bind operator or the shove operator. But it does. I calculated. I don't memorize this stuff.
Mm-hmm.
I just calculated it by looking at what I know that it's about composition. So I go back here and I look at this guy, look at this guy. I say, what is the type of this guy? Well, it has to be something that takes an MB and a function from B to MC and returns an MC. Now when you go to write the code for this guy, if you're going to write this guy in C#, well, you would write select many, and you would end up with the signature for select many.
Huh.
This is how the guys invented LINQ. They say, I need this kind of compositionality. How can I get it? Well, I know mathematically it looks like this. Now I just translate this into C#, and you end up with the... You have to take a function argument. This is why we needed lambda expressions to do LINQ.
Interesting.
Because you have to be able to pass functions as data.
Uh-huh.
We have now inserted functional programming from the arcane ivory tower world of Haskell straight into the industrial, sneakers on the ground world of C#.
Sure.
And F# is the middle ground. It has the performance profile of C#, but will be immediately comfortable to people from Haskell. Or from, the pure ivory
It's
tower.
now a real supported language.
It's a real supported language. It's been announced that this is making lots of people happy.
Yes.
Because you can have your cake and eat it too.
Yep.
You can be as functional as you want. You can be as imperative as you want. This is goodness.
Absolutely.
This is goodness. And it's delightful to me because I've been involved in functional programming for a long, long time. And it's a hard sell. It's a hard sell. And the reason it's a hard sell is immediately on the foundation of computing, 1947, 1950, the world split into two camps, the bottom-up camp and the top-down camp. The bottom-up camp is typified by Turing machines. Let's start with the hardware and add abstraction as we need it to get close to the mathematics, but never at the expense of performance. That gave rise to Fortran and C and C++, and Pascal, and Java, and C#. All of those languages are in that tradition. The top-down crowd says, let's start with the mathematics and subtract abstractions to get down to the machine, sometimes at the expense of performance. That tradition starts with lambda calculus, which is the fundamental mathematics of all this stuff, and only subtracts abstraction when it's convenient to do that. And that's the tradition that gave rise to ALGOL and to Lisp and to Smalltalk and to ML and all these languages that have these, and Haskell, that have these reputations of being slow. But that's because it starts with the math and subtracts abstraction. The other tradition starts with the hardware and adds abstraction. Right now we have the first marketable confluence of these two traditions, and that's F#.
Outstanding.
This is beautiful because, the partisans over here say, oh, don't go to the hardware so early, you lock yourself into irreversible design choices. And this camp over here says, don't give me all this math. I can't handle garbage collection or function calls or whatever it is that's getting in the way of my performance. I need every ounce of performance the hardware can give me. And I'm willing to write software in the wee hours of the morning to get it.
Yeah.
These are irreconcilable differences. This is why they've been divorced for 60, 70 years.
Yes.
But now they're getting back together, and F# is a marketable language, and it's a beautifully done thing.
Absolutely. From MSR Cambridge.
From MSR Cambridge. Our guys.
Absolutely. I'm sure Eric had some input into that as well.
I hope this wasn't too much arcane. What I'm trying to do is show people who have you will encounter monads soon, because functional programming is coming down the road like a triple trailer 18-wheeler with extra.
Yes.
Yeah, it's not 18 wheels anymore. It's what 2, 4, 6, 8.
Big. Yeah.
And you're not going to be able to avoid it. And many people struggle with monads.
Mm-hmm.
And part of the reason is the people who already know it, they just say, oh, it's just a little category theory, don't big deal.
Yeah.
The rest of us say, oh, you mean I got to do another withering 3-semester course in abstract algebra before I can even understand how to use these things? No. It's just function composition in disguise.
Outstanding. And you guys have done a good job disguising it in C#.
That's right.
And VB.
Yeah.
And so, one of the things that I guess people are, because we've been pushing this mantra very hard on Channel 9 over the past few months about the merging of functional constructs that, from Eric and you and other people have thrown into other languages.
Yes.
To help deal with the unreconcilable, or whatever the word is, the fact that you need to have lambda expressions, and now we're learning monads to deal with the future.
Because complexity is killing us,
yes.
And we need to control it. And the way to control it is to put our functions in little groups, little collections where things are disciplined, where you can compose them in arbitrary ways. Build complexity out of simplicity by composing things. Not by adding ad hoc features that need to be bodged into the rest of your construction.
Yes.
That's what's killing us. We add a feature and then we have to fit it to everything else.
Yeah.
Oh, what a mess.
Yeah.
Because those other things don't obey associativity in units. But that's all you need. You put in the associativity in the units and now you can add features fearlessly. You don't even have to know the things that you're going to interact with. The interaction is already built into the structure. Structure it correctly with a simple discipline like this, and you can create anything you want, and it will automatically fit with the stuff that's already there.
Outstanding.
That's what's killing us, is too many combinations, too many interactions. We have to control that side of things. Monads is just a theory for interacting things. Just like as monoids is a theory for interacting things. And it's nothing more than a generalization of clock arithmetic.
Okay. Excellent.
Yeah.
Well, hey, you really, I understand monads to much more than I did when I walked in here today, so I'm assuming everybody else out in the audience does.
That's what I'm trying to do.
And as usual, it's always a pleasure to talk to you.
Always
Brian.
a pleasure. Love seeing you.
And we'll be back here again for sure.
Okay, bring me questions too.
You got it.
Right.
They're going to be on the thread.
That's right. That's right. I can log on
myself. You're an iron now. But I'll
Great.
remind you, you're a busy guy.
All right.
All right. Thank you.
Thank you.